Moving on to lesson 4, using tables to find equivalent ratios. This one's called a trip to the moon. Again, we are working in our M2-T1 ratios tab. We are on 1.4, and the page should look like this, a trip to the moon. If you are working in your textbook, you are looking for this page, M2-57. All right, so we have learned a number of ways to find equivalent ratios. We can draw pictures, we can use tape diagrams, double number lines, use proportions, scale up, scale down. In this one, we look at tables, and this is very often how people organize information to solve a variety of problems. And so we can use what we know about equivalent ratios to help fill in tables, make predictions, and find more information. So in this lesson, we will create and reason about tables of equivalent ratios, solve problems about reasoning. We'll use graphs, diagrams, tables of equivalent ratios. All right, well, let's move on. We're going to skip this getting started, and I want to start right here with 4.1, Introduction to Ratio Tables. It says gravity is a natural force that attracts objects to each other. Gravity is the pull toward the center of an object like Earth, a planet, or the moon. Your weight on Earth is the measure of the amount of gravitational attraction exerted on you by the Earth. The moon has a weaker gravitational force than Earth. The ratio of your weight on Earth to your weight on the moon is approximately 60 pounds to 10 pounds. So what that means, if you weigh 60 pounds on Earth, then you buzz up to the moon really quickly and weigh yourself, you'd really only weigh 10 pounds. So a little weaker gravitational pull. We can use ratio tables to show how to organize quantities. Two quantities are related. Tables are a way to organize information. So this table shows our weight on Earth in pounds and the weight on moon in pounds. So here's that original ratio we saw, 60 to 10. And we can make predictions then about different people's weights and how much they would weigh on the moon. For example, if you didn't weigh 60 pounds, you only weighed 30 pounds on Earth, how much would you weigh on the moon? You'd weigh 5 pounds. And the reason and the way they found this was by dividing by 2, or taking half of it. What if you weighed 90 pounds on Earth? Well, then you'd weigh 15 pounds on the moon. How could I figure that out? Well, a couple different ways. I could say if a person was 60 pounds and 30 pounds and I combine those pounds together to equal a 90-pound person, and I combine these two together, and that person would weigh 15 pounds on the moon. All right. So I've got some different ways to know that I am coming up with the right amounts. Here's another thing I want to point out. If we write down these original ratios like this, 60 to 10, 30 to 5, 90 to 15, and if we treat them like fractions and we simplify them, every single one of these simplifies. Divide by 10. Every single one of these divides down. 30 divided by 5 is 6 to 1. 90 divided by 15 is 6 to 1. They all simplify down to 6 to 1, which is our unit rate or our base ratio. As long as that's happening, we know we're getting the correct information in the table. Another way to figure out what 90 and 15 were, we just added these numbers, but a different way we could have done it. We could have taken this 30 here, and we could have said 30 times 3 gives me 90, and 5 times 3 gives me 15. So I could multiply to come up with it. I could add, although I'm not just adding, I'm adding the same amounts in the same way. Interesting. Okay, let's look at some more. We kind of answered those first two questions. So let's go to question 3. Howard, Carla, Mitsu, and Ralph each determine the weight of a 120-pound person on the moon. Compare Howard and Carla's strategies. Okay, let's take a minute to just see what Howard's doing here. He's got the same table that we set up and saw on the other page with all those three. And it says, I can scale up 60 to 120 by multiplying by 2. So then I must also multiply 10 by 2 to get 20. So he's saying 120 pounds on Earth is 20 pounds on the moon. Makes sense. Carla, on the other hand, she said she also got the ratio of 120 pounds on Earth to 20 pounds on the moon. But what she did was something a little different. She started here with the 30. She said to go from 30 to 120, I could multiply by 4. And then I could do the same thing with the moon weight, multiply it by 4, and 30 times 4 is 120, and 5 times 4 is 20, and that's how she got her ratio. Interesting. So when we compare them, we see Howard scaled up by multiplying by 2, Carla scaled up by multiplying by 4, using that multiplicative reasoning to come up with our answers. Good strategies. I think that makes sense. Well, let's keep going. One other thing I could double check. This new ratio, 120 over 20. I could simplify it, divide by 10. 12 divided by 2 is 6 to 1. Yes, it does meet that base ratio, that unit rate that I was looking for. Let's keep going. Explain Mitsu's reasoning, then verify the ratio 120 pounds on Earth to 20 pounds on the moon is a correct equivalent ratio. Let's see what Mitsu did. I used the weights for a 30-pound person and a 90-pound person to get the weight of a 120-pound person. So that means 120 pounds on Earth is 20 pounds on the moon, because they put together a 5-pound person, 15-pound person. Is that right? Does that work? It does in this case. They were adding these two together to come up with the new ratio of 120 over 20. Makes sense. And we can verify it because we know 120 over 20 does in fact simplify down to 6 over 1. Ralph is incorrect, it says. So he is not correct. Let's see maybe where Ralph went wrong. The difference between 90 and 120 is 30. So I just added 30 to 15 and got 45. So he says the ratio of 120 pounds on Earth is 45 pounds on the moon. But he is incorrect. Well, I know definitely I can multiply. This part I added, but I combined ratios together to make a new ratio. I'm not combining ratios on this one. I'm simply just looking for an additive pattern. But I know that with ratios it has to be multiplicative. So I don't think it works. I can double check though, and I can do 120 over 45. And if I wanted to divide by, to get it down to 6, because 6 over 1 is my unit rate, 120 divided by 20 would give me 6. But 45 divided by 20 is not 1, which is what I want. So Ralph is going to be incorrect because he used more additive reasoning instead of multiplicative reasoning. Better luck next time, Ralph. All right, Mitsu said, I see another equivalent ratio when I look at the way Carla showed her work. I don't know where this writing came from, but let's get rid of it because it's going to mess us up. Mitsu said, I see another equivalent ratio when I look at the way Carla showed her work. 30 pounds on Earth equals 5 pounds on the moon, 120 pounds on Earth to 20 pounds on the moon, 150 pounds on Earth to 25 pounds on the moon. Is Mitsu correct? So she finds another equivalent ratio, this one, 150 to 25. Does that work with our table? Use the table to show a different calculation. All right, let's go back up here to 4. If we combine a 30-pounder person and a 120-pound person, that would be a 150-pound person. If we combined those same weights on the moon, 5 plus 20, we would get a 25-pound person on the moon. Yes, that does match our new ratio of 150 to 25. Most definitely. All right. Use the table to show a different calculation for the ratio of 150 pounds on Earth to 25 pounds on the moon. So we're going to have to add a box here. All right. So how else could we get 150 to 25? In Mitsu's solution, they added the weight of a 30-pounder and a 90-pounder to get a 120er, right? And then they added a 30-pounder plus a 120er to come up with this new one. What's a different way we could do it? Well, I wonder if maybe I could think of something that I could multiply 30 by to get 150. What could I multiply by to get 150? Well, if I ignore the zeros for a second, I could see that I could take 3 times 5. I could scale up and multiply by 5. 3 times 5 is 15. Add my 0 is 150. And I could apply that same thing down here, and I could take 5 times 5 to come up with my 125. So I most definitely, if I had 30 over 5, and to get up to 150, I would times it by 5, times it by 5, to end up with 150 over 25. Let's make sure that this is an equivalent ratio. Let's see. Let's say 5 goes into 15, 30. Get it down to that, and 30 divided by 5 is 6 over 1. So yes, I still get it down to my equivalent unit ratio of 6 to 1. I'm wondering if I could come up with one more equivalent ratio for the chart. Why don't you go ahead and pause this for a moment and see if you can find out one more equivalent ratio. Okay, let's come back. Let's see. We've kind of got a pattern going on the bottom. Times 5. I wonder if I took, instead of scaling up, if I take this original ratio and I scale up times 6 instead of times 5, what will that get me? Let's see, 30 times 6 is 180, and 5 times 6 is 30. So a 180-pound person on Earth is equivalent to a 30-pound person on the moon. I think that works. To double check, I'm going to simplify. Divide by 10, and 18 divided by 3 is 6 to 1. I think my strategy works. Let's move on to using tables to come up with equivalent ratios. Not sure why I have all this writing on here. All right, the 6th grade pizza party is planned for tomorrow. Tracy's in charge of ordering the pizza for 450 students. Pizza parlor said 2 pizzas serves 9 students. Tracy made a ratio table to help her determine how many pizzas to order for 450 students. That's a lot of kids. Explain Tracy's strategy and determine the number of pizzas needed. I'm going to let you think about this for a second. Why don't you pause this video and see if you can figure out what she's doing in this ratio table and how many pizzas will be needed for 450 students. Okay, hopefully you made some connections here. They even drew some arrows to help you out. So to go from 2 to 10, that would be multiplying by 5. Let's check and see if that works for down here. Multiplying 9 times 5 gives you 45. Well, to go from 45 to 450, that looks like they multiplied by 10. So if you do the same up here, and you multiply your 10 times 10, that would give you 100 pizzas. So I think Tracy will need to order 100 pizzas. Quite a few for her class, for sure. Complete the table to show the number of pizzas to order given the number of students. So if we don't have 450, or we have way more than 450 like you can see here, how many pizzas are we going to have to order? And then explain your calculations. Go ahead and pause the video now, do some figuring to come up with your answers, and then meet me back here once you've got them done. Okay, hopefully you started to make some connections in how we came up with the number of pizzas. We first saw an example of multiplying by 5, and then we saw an example of multiplying by 10 to come up with our 100. And then we've got to make some more predictions from there. So, for example, we could say, we've got 135. We're going to have to come up with something that's going to help us get from these numbers to 135. So if I look for a pattern here, and I think about what could I multiply 9 by, does 9 go into 135? Let me see. 135 divided by 9. You get minus, you get 4, bring down your 5. 9 goes into 45 5 times, and you get 45. All right, so I know that if I take 9 times 15, I can get 135. Well, that's great. That must help me get up here, and I can take 2 times 15 to get 30. I think that works. Definitely going to be an equivalent ratio. What other patterns can I see? Starting to kind of notice this is times 5, times 10, times 15. I also notice if I go from 450 and I double it, 450 times 2 gives me 900. That's one I can kind of do in my head. So if I times that one by 2, I can come up here and take 100 times 2 and get 200. Okay, that makes sense. That makes sense to me for sure. Where else could I make some patterns here? Let's see, 135 times 2 is 270. Oh, I see a pattern there. 135 times 270, or 135 times 2 gives me 270. So that's just like doubling it. So I bet I could come up here and double it and get 60. Okay, we're making some progress now, I think. Where else can I see some similarities? Let's see. 225. I'm wondering if I put 45 here. What can I multiply 45 by to get 225? I'm thinking 5. Let's see. 5 times 4 is 20, plus 2 is 22. So I can multiply 45 times 5 to get 225. That must mean I can multiply 10 times 5 to get 50. All right, now we are talking for sure. So now I just have to make one last prediction here on how I can come up with this last one. Now, if I was to combine 450 students and 900 students, if I was to combine that student body together, 900 plus 450 gives me 1350. Oh, bingo. So that means if I add this amount of pizzas plus this amount of pizzas, gives me a total of 300 pizzas for 1350 students. Okay, not bad. It takes us some try and check, and some reasoning to think about this, but we were able to get our table complete. So let's answer our questions now. How many students will 12 pizzas feed? 12 pizzas. Well, I know that the first ratio, 2 pizzas feeds 9 students. And then if I have 10 pizzas feeding 45 students, so it's 12 pizzas altogether. So if I take these 2 pizzas and these 10 pizzas, that's 12 pizzas, correct? And if I add those students together, then I end up with 54 students. That makes sense to me. Let's also see 10 pizzas. Okay, how many students will 20 pizzas feed? Well, I need 20 pizzas, and here's 10 pizzas right here. So the ratio is 10 to 45, plus another 10 pizzas to 45. That gives me 20 pizzas total, and it means I can feed 90 students. So we can reason our way through this graph to help us answer questions. And finally, how many students will 90 pizzas feed? This one might be a little trickier. Let's see. Could I go with my ratio? I like to work with the tens. I could use some different ones, but let's say 10 pizzas serve 45 students, and I have 90 pizzas. So if I times it by 9, 10 times 9 is 90, that would be 90 pizzas. And 45 times 9 would be